Hi, I'm very glad to present our work about StreamQL, which is a query language proposed for processing streaming time series. My name is Lingkun, and this is joint work with Konstantinos Mamouras. Recent advances in IoT technology are causing a huge amount of data being generated in real time. Such data arise in several application domains, including healthcare monitoring, smart building, smart grid, and etc. These data are typically collected from sensors, and we can view them as streaming time series. It's challenging to process the streaming time series. As a huge amount of data arrive in real time, we cannot store and process the data offline. Also, the processing speed has to be very fast, as the data is generated at a very high rate. Moreover, the processing may involve complex computations. For example, let's consider real-time healthcare monitoring applications, which typically have a huge amount of data, as the signals might be collected from many sensors with a high sampling frequency. Such data typically contain noise from many sources, and these data are mostly uneventful, but they also contain episodes of unusual activities. So we want to find these abnormal events and issue real-time alerts. So the typical computation needs to reduce the noise, identify abnormal signal patterns, and summarize the most important information to issue real-time alerts. To make this example concrete, we want to detect the heartbeat for a patient based on a stream of signal measurements. And such computation requires the detection of peaks from the ECG signal. And here is an example of ECG signal, where the red markers are the peaks that we are going to detect. One algorithm for ECG peak detection involves the following computations. First of all, we smooth the signal to reduce high-frequency noise. Then, we calculate the derivative of the smoothed signal. And finally, we find the ECG peaks according to some decision rules. A natural approach to developing such an application is to write the algorithm in a general-purpose programming language, such as C. But this requires programmers to figure out what exactly a state to maintain, how to update the state for each input item, and how to produce the output. So I argue that this is cumbersome and error-prone, and this does not facilitate the modular description of complex computation. In this case, a lot of specialized languages, compilers, and runtime systems are proposed to deal with the processing of streaming data. For example, relational database systems have been adapted to the streaming setting, like Stanford Stream. And several systems, such as Storm and Spark Streaming, have been developed for the distributed data stream processing. Languages like SAS and Cayuga have been proposed for detecting complex events. And synchronous data flow programming languages, such as Lustre, are related to stream processing. Moreover, there are tools for reactive programming, like ReactiveX. And there are several projects about processing real-time signals, such as XStream. Depending on the application, each approach has its own strength. For the application we are interested in, the language needs to integrate various streaming constructs to describe the computation. For example, in ECG peak detection, the computation that smooths the signal and calculates the derivative typically requires the relational constructs like map and window. The computation that detects a peak needs a temporal construct to analyze the temporal pattern of the signal. And finally, to compose these computations together, data flow constructs like streaming pipeline need to be involved. In general, to describe computations for processing the streaming time series, we find it is essential to integrate the relational, data flow, and temporal constructs. So in our proposal, we designed StreamQL that has a rich set of streaming constructs. The key design choice of StreamQL is it identifies an appropriate programming abstraction. That is, we base the language on the abstraction of string transformations. In other words, StreamQL is an algebra of string transformations. Its basic elements are string transformations like filter, map, and streaming aggregation, and its combinators are operations on string transformations like window and pipeline. Based on this abstraction, StreamQL allows all its language constructs to be composed freely, and it has a formal denotational semantics. Finally, this abstraction enables a very lightweight implementation of StreamQL. In this presentation, I'll first give an overview of the StreamQL language, which includes the concept of stream transformation and several of its language constructs. Then, I'll show how to use StreamQL to program the ECGP detection algorithm. Finally, I'll show the experimental evaluation. So we start with introducing the semantics of the data stream. Typically, a data stream is viewed as an unbounded sequence of data items. However, there are situations where a stream could terminate. For example, the program may read lines from a storybook as input. As story eventually will end, the input stream will terminate as well. To allow the program to respond to the end of string, we extend the definition of data stream to be a sequence of data items with a potential and string marker. Here we use a rectangle to represent the end string marker and use the parentheses to indicate that the stream may or may not end. So suppose the type of the data stream is A. We can use A star to represent the type of a sequence of data items. Then we use a special square symbol to represent the end string marker. So we can define the type of the data stream as a data sequence with a potential and string marker. And we further use A stream to represent this type, which is abbreviated as AS. In the processing of data streams, with the arrival of each input item, the program produces an arbitrary number of output items, and the input stream is monotonically transformed into the output stream. Therefore, we can use stream transformation to describe the streaming computation. Let's consider the type of the input stream is A stream and the type of the output stream is B stream. We can formalize the stream transformation as a monotone function from A stream to B stream, and we can give a formal denotational semantics to StreamQL using these monotone functions. Now, let me introduce some of StreamQL's language constructs, and I will first introduce the map construct. Given a mapping function, the map construct applies a function to each input item. In this example, the input is a stream of integers, and the mapping function is given as a lambda expression. Here, the input stream may contain an end string marker to indicate that stream is terminated. In this case, the program can simply echo the end string marker to indicate there will be no further output. StreamQL also provides a construct that describes a computation as a pipeline of stages. For example, here, the output of query F is passed as the input to query G. Now, let me introduce the temporal sequencing construct. This construct can apply different queries one after the other, thereby varying the computation over time. In this example, the query F will first process a string. Then, after F terminates, the query G starts and processes the rest of the string. Finally, we introduce the construct for temporal iteration, and this construct can be used to repeat a streaming computation indefinitely. In this example, we repeat the query F to perform the computation, and whenever F terminates, it will be restarted to process the rest of the string. The temporal sequencing and the temporal iteration can be viewed as stream transforming analogues of concatenation and cleaning star. Now we have introduced the basic language primitives. Let's go back to the problem about ECG analysis and use StreamQL to specify the computation. As we mentioned, there are 3 stages of computations, and we can represent them as the smooth, the derivative, and the detect queries. Therefore, we can describe the computation as a pipeline. Then, let me focus on the stage of detection and discuss how StreamQL provides facilities to program the algorithm. In this figure, we show the intermediate outputs of the algorithm, where the gray line represents the raw signal, the green line is the smooth signal, and the blue line is the derivative signal. So the algorithm starts by searching the data whose derivative is larger than a high threshold. Then the algorithm takes the data until the derivative is lower than a low threshold. After that, as the region of a single peak is determined, the algorithm computes the argmax of the raw signal to get the ECG peak. So here we can use temporal sequencing construct to perform the ignore and the take queries one after the other. As the found1 peak query has detected the first peak in the signal, we can use the temporal iteration construct to repeat this query and find all peaks in the signal. So far, we have shown how to use StreamQL to encode the ECGP detection algorithm. Now let me talk about the experimental evaluation of StreamQL's implementation. We have implemented StreamQL as a Java library and compared it with 3 popular libraries, OOPSLA, Reactor, and CD. These libraries are all developed in Java, and they are open source and widely used in real-world applications. We have tested the performance of StreamQL in 4 benchmarks. These benchmarks include a micro-benchmark concerning basic streaming computations. The other 3 benchmarks are related to realistic workloads. The stock benchmark detects the stock patterns. The TAQ benchmark analyzes the high-frequency trading data. Finally, the next mark monitors an online auction system. Here we summarize the throughput speedup of StreamQL compared with other libraries. The results show that StreamQL has a competitive performance. One important feature that brings StreamQL a good performance is that StreamQL reduces the overheads brought by the construction of intermediate streams. For libraries like OOPSLA and Reactor, they are based on the abstraction of streams. Here, we present an example query in libraries like OOPSLA and Reactor. The basic object in such libraries is the data stream, and their streaming constructs are operations over data streams, like map and filter. When the query partitions the stream, intermediate stream objects are created to represent the partitioned streams. And this will bring computational overheads. In contrast, StreamQL avoids such overheads. For example, we use a tumbling window to split a stream into non-overlapping regions and apply a query to elements in each region. For libraries based on the abstraction of streams, a new stream object will be created every time when the window is full. In StreamQL, each query denotes a stream transformation. So every time when the window is full, we can simply reset the state of the query and let it keep processing the rest of the stream. And this is more efficient than creating new stream objects. In summary, today I introduced a language called StreamQL for processing streaming time series. This language is simple but expressive, as it integrates relational, Dataflow, and temporal language constructs. Also, it has a formal denotational semantics. Moreover, This language has a lightweight Java implementation, where the efficiency is validated by experiments.